Today I'm going to talk about one of the earliest equations in fluid mechanics which helped us to find an algebraic equation in the framework of continuum mechanics to describe the motion of a fluid, which is called the Bernoulli's equation. Around, I think, 2 centuries ago, the Bernoulli presented this celebrated equation. The Bernoulli's equation has many assumptions, different assumptions, and the procedure of derivation of this important equation is very important. If you want to correctly use this equation in correct situations, you have to be aware of assumptions behind this equation and the procedure of derivation of different forms of this equation. Okay, let's start from the first equation, or the first version of the Bernoulli's equation, which can be used for irrotational flows. The irrotationality is related to the vorticity vector. When I say the flow is irrotational, it means that the curl of a velocity or the vorticity vector is 0, or the velocity field is curl-free. And also the flow is compressible, but the flow can be viscose. It's important to be aware that the Bernoulli's equation can be written for viscose flows when the flow is irrotational and incompressible. And also, in addition to the assumption of viscose, generally viscose, having a viscose flow, the viscosity, the dynamic viscosity, should be constant. So this version of the Bernoulli's equation is written for generally viscose flow with constant viscosity and incompressible and irrotational flow. Also, you say that the Bernoulli's equation can be written between 2 points located on a specific streamline. This version of the Bernoulli's equation can be written between any 2 arbitrary points in the flow field. So we don't have that assumption between 2 points on a streamline here, and you can write the Bernoulli's equation between any 2 points you want. Okay, let's start from the Navier-Stokes equation. Now you see that this term here is the viscose term, so I included the viscose term in the Navier-Stokes equation. So the flow is viscose. This one is the local derivative or local acceleration. This one is the nonlinear term or the advection term. The pressure term, the viscose term, and the gravity force or the volumetric source term. I want to use 2 important identities, vector identities here. The first one is related to the nonlinear term here. You see that I have written the nonlinear term as a sum of 2 terms. The first one is the gradient of the square velocity over 2. And the second one is the lambda vector. This is called the lambda vector, which is the cross product of the velocity and the vorticity. And the vorticity is the curl of the velocity field. And the Laplacian term, which is the viscose term for incompressible and constant viscosity fluids. The Laplacian term, again, can be written as the sum of 2 terms. The first one is gradient of the divergence of the velocity, which is 0 because the flow is incompressible, and the divergence of the velocity field is 0. And the second one is the curl of the vorticity vector, and the vorticity vector itself is the curl of the velocity. So this one is the curl of the velocity field. Substitute these 2 identities into the Navier-Stokes equation. The Laplacian term is converted into this one, which is written here in the right-hand side. We have viscosity here. And the nonlinear term is written as a sum of 2 terms. Keep the first one in the left-hand side, and the second one is written here in the right-hand side. Don't ignore the density here. This is the lambda vector, as you see. Also, we have three terms. This one, the pressure force, and the gravity force, which all of them can be written as gradient of something. For example, the gradient of pressure, gradient of the, I don't want to call it kinetic energy, but something similar to the kinetic energy, and gradient of the z coordinates. So combine these three, this one, and this one. Combine these three terms which are similar to each other because all of them can be written as a gradient of something. In the first, and write them in the first side of the equation. This is the local derivative or local acceleration. And the second part, the second side of the equation include the vorticity vector, as you see. This is the lamp vector, and this one comes from the second identity. So then now it's the time to impose our main assumption, which is the irrotationality of the flow field. So it means that the vorticity vector is a zero. So both terms in the second side of the equation are zero because they both of them include vorticity. So only we have the first side of the equation, which is written here, but consider that in irrotational flows, we can write the velocity vector as gradient of a scalar field, which is called the potential function. Okay, so substitute the velocity vector here by the gradient of the potential function. You see that the order of derivation with respect to time and the gradient operator can be interchanged because the flow field is continuous and continuum mechanics principle holds. Okay, then we have the partial derivative of gradient of phi, or the gradient of potential function, and gradient of these terms. Then integrate this equation between any 2 points, for example. Then you can easily eliminate the del operator or the gradient operator and write this term by the partial derivative of the phi function and sum of the pressure. This is something similar to the kinetic energy, but originally it is the inertia term in the nonlinear advection term. And this is the gravity force. The zero in the right-hand side of the previous equation changes to a constant because you have integrated the equation. This constant generally is a function of time because the flow is unsteady. This form of the Bernoulli's equation is the unsteady Bernoulli's equation for irrotational, incompressible, but viscose, constant viscosity flows, which can be written between any arbitrary pair of points in the flow field. Please consider in this version of the Bernoulli's equation that the flow should be irrotational or potential and viscose. We have a kind of fluid flow which is called the viscose potential flow. This is a keyword, you can Google it and find other details about the viscose or viscose potential flows or viscose irrotational flows. So if someone asks you about the validity of the Bernoulli's equation for viscose flows, the answer is yes. The Bernoulli's equation can be written for a viscose but irrotational and incompressible flows between any arbitrary pair of points. The second version of the Bernoulli's equation is for the ideal flow. Ideal flow, based on your knowledge in basic fluid mechanics, the incompressible and inviscid flow is called the ideal flow. Ideal flow is something different from the ideal gas or perfect gas. This is a name which is used for incompressible and inviscid flows. And during the derivation of this version of the Bernoulli's equation, I won't speak about the vorticity vector or the rotationality or irrotationality of the flow field. So the flow needs to be ideal, incompressible and inviscid, but the flow, in the meantime, the flow can be rotational. So let's go on. And also, this version of the Bernoulli's equation is written between 2 points which are located along a specific streamline. In this version, this assumption is eliminated. So you can write this version of the Bernoulli's equation between any 2 points. But here it's essential to add this assumption, and the final equation is only valid between 2 points located on a specific streamline. Okay, this is the Euler's equation because the flow is inviscid and the viscose term is 0 here, so the Navier-Stokes equation without the viscose term is called the Euler's equation. This is the local derivative or local acceleration. This is the nonlinear term, the pressure term, the gravity force. Again, I expanded this term, the nonlinear term, using this vector identity here. This is the gradient of the kinetic energy, or the square velocity over 2, minus the lambda vector. You see, this is the lambda vector. Okay, the Euler equation, or the Viscose equation, or the Navier-Stokes equation are both vector equations. It means that all terms in the Navier-Stokes equation are vector. This is a vector. This one again is a vector, and so on. But Bernoulli's equation is a scalar equation. So, if I, again, you know that the dot product of two vectors is a scalar quantity. So, I want to compute the dot product of this vector equation, which is the Euler equation, and the ds vector. S coordinate is a coordinate which is defined along the streamline. This is a streamline, an arbitrary streamline. F coordinate, as you see, is defined along the streamline tangent to it. So, this is the velocity. The streamline is tangent to the velocity vector, and so the velocity vector and the S coordinates are parallel to each other. So perform the dot product of the ds vector and the Euler's equation, and then integrate the final scalar equation. The first one here, the local derivative or local acceleration. This is the dot product of the time rate of change of the velocity and the ds vector. The second vector, use this identity here. I have nothing to do with the gradient of the square velocity over 2, so write it here. But the lambda vector, you know the cross product of two vectors is normal to both of them. So the lambda vector is normal to the velocity vector and the vorticity vector. On the other hand, the s is parallel to the velocity vector. And again, you know that the dot product of two vectors, which are normal to each other, is 0. So the ds vector is tangent to the streamline. The velocity vector again is tangent to the streamline, and the lambda vector is normal to the velocity. So the lambda vector is normal to the ds vector. So the dot product of the ds vector and this part of the nonlinear term is a 0. So this way we can get rid of this part of the nonlinear term. In the previous section, the lambda vector was a 0 because the flow was irrotational, but here the flow is rotational. The vorticity vector is not 0. But the dot product of the ds vector and the vorticity vector is 0, and then the equation is just valid along a specific streamline. But in this version, there isn't such a function about the validity of the equation between 2 points on a streamline. Okay, so the dot product of the ds vector and the second part of the nonlinear term is 0. We have gradient of pressure here, gradient of the z coordinate here, and the gradient of the velocity here. So combine them in one term. So this is again the first term, and this is the integration along the streamline of the gradient of 3 terms. Dot ds equal to 0. Okay, let's go on. If you have an integral of gradient of something ds, you can easily write that term as the integration of total change of those quantities equal to 0. And integral of total change of something can be written in, again, that quantity, you see here. Consider here that the velocity is tangent to the streamline. Again, the ds vector is defined tangent to the streamline. The dot product of two vectors which are parallel can be eliminated because the cosine of the angle between them is 1. So eliminate the dot product and also the vector lines above them. So we have the integration of the partial derivative of v with respect to time, or the local acceleration, along a streamline. But the 0 changes to a constant. This constant is a function of the time because the flow is unsteady, as you see, and a stream function. A stream function is a scalar quantity which is constant along a streamline. The stream function is a tag which is used to determine which stream function you are talking about. Okay, for example, this streamline here corresponds to the stream function equal to, for example, to 0. The other streamline corresponds to another value for the stream function. So the constant of the Bernoulli's equation in this version is a function of the stream function, or the function of the stream function which you are writing the equation along it. You see the integral here is an indefinite integral. So you can change this form of the Bernoulli's equation to the definite version. It means that you perform the integration between two specific points on that streamline. The first point is 1 and the second one is 2. So this indefinite integral changes to the definite integral between points 1 and 2. And this package is written here for point 2. And again, copy and paste this package here, but the subscripts are 1. This is the definite version of the Bernoulli's equation for incompressible, inviscid, but generally rotational flow between 2 points which have to be along a specific streamline. The other point here is that the second version of the Bernoulli's equation, which is used for ideal flows, is engaged with a stream function. Because this version is written along a streamline, and along a streamline, the stream function is a constant value, is a constant parameter. So you see the stream function appears here. But the first version of the Bernoulli's equation is engaged with the potential function, because the potential function can be just defined for rotational flows. Here the flow can be rotational. So you can use the phi or the potential function in this version, but you see the psi appears here. Another point here is that let's expand the nonlinear term in Cartesian coordinates, for example, or in coordinates one of which is tangent to the streamline S, and the other one is normal to the streamline. So the advection term can be written as the Vs as the component of the velocity in the S direction, and Vn is the component of velocity normal to streamline direction. Vs, partial derivative of Vs with respect to S, Vn, partial derivative of Vs with respect to N. You know that velocity is tangent to the streamline, so the velocity component in normal to streamline direction is 0. So the second term vanishes. Vs, partial derivative of Vs over S can be written based on your basic mathematics knowledge, and the partial derivative of S square velocity over 2. So this is the same term as appears here, or in the first identity. So you see that because the velocity is tangent to the streamline, the second term in the advection nonlinear term is 0, and the nonlinear term can be written as the derivation of, I don't want to call it the potential, the kinetic energy, but something similar to the kinetic energy, which is the inertia force. The version of the Bernoulli's equation is the compressible form of the equation. You see, this is similar to the original version of the Bernoulli's equation. There is one difference. Here we have the integral of the pressure force when we are integrating the Navier-Stokes equation or the Euler's equation. The integration of all terms appear. This is the integral of the pressure term. You see we have the density inside the integral. So when you are going to compute the integral, it's important to know the dependency of the density and the pressure. So you know the density is a function of pressure. If the flow is incompressible, density is not a function of pressure, so you can reduce this integral to the well-known Bernoulli's equation, which we have P over density in the equation. But here I'm going to compute the integral. So in compressible flows, for example, gases sometimes act as compressible flows at Mach numbers greater than 0.3. I have to pray the thermodynamic process which the gas experiences. So when I say the flow is compressible, the dependency of the density and the pressure is dependent of the thermodynamic pressure. One of the most important and most common thermodynamic processes is the isentropic process. Since many different applications are adiabatic and are also reversible, so we can say that the isentropic relation, which says that we have such a relation between the pressure and the density, can be used to describe the reversible and adiabatic process. Because the flow is inviscid, we can say that irreversibilities coming from viscosity vanish, and also we don't have heat transfer because we are writing the conservation of momentum, not conservation of energy. So we can say the process is adiabatic and also reversible and consequently isentropic. This process of derivation of the final form of compressible Bernoulli's equation is similar to what we do in thermodynamic relations, in obtaining different relations and working with different thermodynamic parameters such as pressure and density. You see, V-rho refers to a known condition or a reference condition. So P over rho to the power of gamma. Gamma is the specific heat ratio or the isentropic index. So the other process, the process of derivation of the final relation is straightforward. There is nothing important. You can follow relations. You see here we have the integration of inverse of density with respect to pressure. So you have to find the inverse of density from this relation. So as you see, the inverse of is equal to this expression, and then perform the integration and substitute this form in this expression in the equation. So the integral of Bp over rho is equal to integral of this expression dp. And here again, this term, the integral of dp over rho, this is these p0 and rho 0 are constants, and perform integration. So you can finally obtain this expression here, and then substitute from the original definition here to omit zero quantities, and you can finally obtain that the integration of dp over rho is equal to the gamma over gamma minus 1 p over rho, and then substitute this final result into the compressible form of the Bernoulli's equation. So we can say that this term here again copy and paste, and these the two terms are again copy and paste here, This form is the only difference between the compressible and incompressible Bernoulli's equation. As you see, we have a factor here, gamma over gamma minus 1. Gamma is the specific heat ratio Cp over Cv, which is equal to 1.4 for air, for example, in standard temperature and pressure, equal to constant. This constant again is a function of the stream function and time. Fourth version of the Bernoulli's equation is called the Bernoulli's equation in a relative motion. You know, we have, because the Bernoulli's equation is a result of the conservation of momentum, and we have accelerations in the conservation of momentum. If two different frames, for example, one of the frames is rotating in a circular motion, for example, so we have two different frames. The first one is the one which is attached to the stationary observer, and the other one is attached to the motion of the control volume or the system or the device. In such cases, we have three velocities. The absolute velocity, which is measured with respect to the fixed observer, the relative velocity, which is measured with respect to the coordinate, which is attached to the moving frame, and the third one, the velocity of the moving frame itself. Similarly, we have some relative accelerations, such as the Coriolis acceleration and the centrifugal or centripetal acceleration. So, in the derivation of the standard form of the Bernoulli's equation, for example, this one, we have ignored the existence of such relative accelerations. If you include the centripetal acceleration or the centrifugal force in the procedure of derivation of the Bernoulli's equation, the final equation is the Bernoulli's equation in relative motion. This form of Bernoulli's equation is frequently used in analysis of different flow in different rotating machines, for example, pumps and compressors, especially in incompressible, because you know one of the main assumptions of the Bernoulli's equation is the incompressibility. So this equation, which is the Bernoulli's equation in relative motion, is frequently used in the analysis of fluid motion in incompressible machines, for example, pumps. Here we have, as I told you, we have three velocities. U is the velocity of the motion of frame. For example, in a centrifugal pump, the impeller rotates with a specific angular velocity. So U is the peripheral velocity, which is the product of the radius and the angular velocity. W is the relative velocity, which shows the motion of the fluid between blades of the impeller, between the flow passages, between the blades. If the angular velocity of rotation of the pump reduces, the magnitude of the centripetal inertia or the centripetal acceleration reduces. If the pump stops, then this term vanishes, and again the W, which is the relative velocity, will become absolute velocity. So you can replace W with absolute velocity and omit this term when we have no relative motion. So this equation reduces, in this limiting case, that equation reduces to the standard form of the Bernoulli's equation. Okay, in the fifth version, I have written the simplest form of the Bernoulli's equation. Here we have neglected the unsteadiness, the compressibility, or the relative motion, etc. And I have written the simplest standard form of the Bernoulli's equation. This form, I call this form the pressure form of the Bernoulli equation, because as you see, the dimension of each term in the equation is the dimension of pressure, or the unit of each term is the unit of pressure, which is Pascal, for example, in SI system of units. So the first term is the static pressure because it has nothing to do with the velocity. The second term is the hydro the static pressure which appears in a fluid which is at rest. And the third term is the dynamic pressure. As you see, this is not pressure at all. This is a combination of the density and the velocity, but because of its dimension, which is the dimension of pressure, we call it the dynamic pressure. The name shows that it's related to the velocity, not to the pressure. Okay, the sum of the first and the third term, or the static and the dynamic pressure, is called the total pressure, or the stagnation pressure, because it's equal to the static pressure of a fluid, which its velocity becomes zero, or becomes stagnation pressure. If you omit the third term, which is true for a fluid at rest, and the velocity is equal to zero, so you can see that the pressure, static pressure, is equal to the minus hydrostatic pressure plus a constant. This is exactly the hydrostatic pressure distribution in a fluid which is at rest. The sixth version of the Bernoulli's equation is exactly similar to the fifth version, but this time I've divided both sides of the fifth form by the density, or each term in the fifth form is written per unit mass. So as you see, the dimension or the unit of each term in the fixed form is totally kinematic. And you don't see, for example, a kilogram or a Newton or something related to mass or force. And the seventh version of the Bernoulli's equation is similar to the fifth version, but this time divide both sides of the equation by the specific weight or gamma. This way, each term in the equation will become something similar to length, or the dimension of each term in the equation is the dimension of length, because such quantities, for example, head, because this is the pressure head, this is the dynamic head, or the velocity head. And the sum of two first terms in this equation is called the stagnation head, or the total head. In different engineering applications, it's more appropriate for us to use this form of quantities. I mean the head form with the dimension of length. Eighth form of the Bernoulli's equation is sometimes called the modified Bernoulli's equation, but I will explain that this title, the modified Bernoulli's equation, is not appropriate for this situation. The first equation is the standard form of the Bernoulli's equation, and the simplest form, written between 2 points, point 1 and point. This is the pressure force. This one is the inertia, or the acceleration. And the third term is the gravity force. And the second relation is the conservation of energy, again written between 2 points. This time, the first term is the work done by the pressure. This was the pressure force. This is the work done by the pressure force. The second term, this time in this equation, is the kinetic energy. This was the inertia. This is the kinetic energy. The third term was the gravity force, but here the third term is the potential energy. As you see, the Bernoulli's equation and the conservation of energy are very similar to each other, but the energy equation contains 3 extra terms which are not included in the Bernoulli's equation. The origin of this difference is that the Bernoulli's equation is the conservation of momentum. It's not expected to see for example, the heat transfer rate in the conservation of momentum, because the heat transfer rate is a quantity which is related to the conservation of energy. So, but in the conservation of energy, or the energy equation, we have the difference of the internal energy of the fluid, or we have the heat transfer term, and the work exchanged with the surrounding. So these 3 extra terms should be explained. If you omit these terms, the energy equation will be exactly similar to the Bernoulli's equation. The positive and the minus sign here refers to the device, for example, a pump or a compressor and a turbine. The turbine extracts the work from the system, and devices such as pumps and compressor inject energy to the system. So the positive sign here is for devices such as turbines, and the minus sign is for pumps and compressors. If the first hand side, which is again written in the head form with the dimension of length, is the sum of the pressure head, the kinetic energy head or the velocity head, and the potential energy. This package is called the mechanical energy or the total energy or the mechanical head or the total head. This is the content of energy in the input, which is shown by subscript 1, and this is the content of energy in the exit, for example, shown by the subscript 2. You see the content of energy from point 1 to 2 changes because of two origins. The first one is related to the devices such as turbo machines, pumps and turbines. Let's ignore this term. And the other one is related to the exchange of heat between the system and the surrounding. And this one is the increase of the internal energy. As you know, the internal energy is related to temperature, so it's related to the increase of temperature of the liquid, for example, or the gas. From a practical viewpoint, the increase of temperature of a fluid is not appropriate for us. So this term is the waste of energy, or the loss of energy, or the dissipation of energy, which is always positive based on the second law of the thermodynamics. But this term can be positive or negative based on the direction of the heat transfer between the system and the surrounding. So the sum of this term is called the dissipation or the head loss, because the dimension of both of them again is the dimension of length. This is the turbine head or the pump head, which can be added to the system or extracted from it. This one is the head loss, because the increase of the temperature is not appropriate for us. It's the waste of energy, unwanted waste of energy, but this term can be positive or negative for the dissipation of heat. For example, if you touch the compressor behind the refrigerator, you understand that it's hot. The high temperature of that compressor leads to the dissipation of heat based on different mechanisms of heat transfer, such as radiation or convection or conduction. So this term is called the head loss. So the total content of energy in the head form in the entrance, or the point 1, is equal to the content of energy at the exit, or point 2, plus or minus the added or the extracted energy, or the head, in turbine, pump, compressor, and other similar devices, and the rest of energy should be wasted based on the dissipated, or which is called the head loss, based on the conservation of energy.